Hello everyone. Today we will start the introduction to our course materials. So we made introduction to the course in general, but this is a revision of the electrical three-phase circuits and power calculation. So this is going to be very important, guys, for anyone who didn't take the courses of three-phase AC circuits, or also like revision for who had these courses. And we will focus also on the power and power factor correction. So this topic is very important. And we will have some topics in our electrical machines related to that power factor. So most of the AC machines, you will need the power factor calculation. So please, this part is very important. If you have any questions in this part after this class, don't hesitate to contact me. This has to be crystal clear for all of you guys, because this is like one of the important basics for electrical engineer in order to understand the work in AC or electrical power. So let's see together, guys, the objectives and topics of our class today. So here are the objectives of our class. The objectives are as follow: to discuss the power factor correction, review the three-phase systems, review the different three-phase connections, review the transformation between star and delta. Star is the Y connection, so we call it Y or star. And also review the power measurement methods used for three-phase circuits. So these are the objectives and topics that we will cover today. If we couldn't cover this in one session due to the time limitation, we will make it, or we will continue in the coming session. Okay, let's start, guys. Firstly, to see what is the power in AC circuits. So, firstly, if we have a cup with this drink inside, I'm sure that all of you know that the part that will be drinkable is this lower part only. So this is a useful work. In power, you know that useful work is measured in watts. And you know the upper part is nothing but wasted capacity, which means we don't use it, or it's not useful for the guy who will drink this cup. But by the end, it has to be in the cup because it's already has part of the overall capacity of the cup. So this is a simplified example for the active and reactive power. But one thing, guys, is you cannot have the useful part here of power without having the reactive power. So this is like very important part to understand the concept of AC power. So with AC power, you cannot have the active power without the reactive power. Simply, we can say reactive power, guys, is the main way to control the active power flow. So we control the active power flow by means of reactive power. If you don't have reactive power in your AC network, you don't have control on your power. Okay? So this is from the point of view of power generation and transmission. Reactive power is very important. But for a customer, So the customer has the device which is measuring the power consumption at home. So this device is measuring energy, not power. It's measuring energy. And you know that energy equals power times time. So since the active power is measured in watts, so we expect that the energy is watt seconds. So this is the main unit of energy. So the device that measure power at home, we call it kilowatt hour meter. Kilowatt hour meter. Watt hour is power times time, and we made it in kilo because it's large value. So this is the name of the device, kilowatt hour meter. So we expect that along with the kilowatt, we will have some kilovar. So you will have some kVAR of power, which is the measure of the part of the reactive power here. And the total power is going to be in volt ampere. And again, we refer it in K because it's a huge amount. So this is going to be in kilowatt, this is going to be in kilovars, and the total is in kilovolt ampere. This is a simple example, and I know all of you guys already learned the meaning of active and reactive power in AC circuits. So, you know, guys, that active power, let me write that down here. So, active power will be absorbed from resistive load. So, this is the part of power that will be absorbed on resistance. So, all type of resistive loads will consume active power. So where the reactive power is going? The reactive power actually is going between inductance and capacitance. Inductance takes reactive power and capacitance delivers reactive power. So this means in your circuit, if you have inductive reactance and capacitive reactance, someone will take reactive power and the other one will deliver reactive power. If both of them are having the same amount of reactive power, this means the net reactive power in your system is zero because the direction of every reactive power will cancel each other. And then the total power will be only active power. So this is just a revision on the part of the active and reactive power that you learned already in electrical circuits. Now let's see the power factor improvements. Firstly, guys, why do we need power factor improvements? Let me show you that through a solved problem. So we will have solved problem right here. And from the solved problem, you will figure out why do we need to make power factor correction. But power factor correction is very beneficial to the company that delivers the power to you. There is no benefits for the customers from the power factor correction. But some customers, like factories for instance, if they do not make power factor correction, they will have some penalties. These penalties can be several or a lot of millions of dollars. Okay, guys, so it's not an easy like to leave the power factor without correction. So this is very important in industry and very important for the transmission systems. Why? We will answer this question in the numerical example. But firstly, let's see, guys, how can we make power factor improvements? So if you have a certain load, let's say inductive loads, because the majority of our loads are inductive. If you, for instance, at homes, you will have some motors in your fridge, in your machines, in your air condition. So all of these devices have motors. And motors will have coils, and these coils will take reactive power. I don't like to say absorb reactive power because reactive power is not absorbed. Only we can say active power is absorbed. So reactive power is oscillating. So it will be taken through inductive and returned back again through capacitive. Okay, so we don't say consumed or absorbed. Okay, consumed or absorbed is only for active power. So these inductive loads will take some reactive power and already absorb the amount of active power needed for your load. So we absorb here P and take Q. If I added a capacitor here, this capacitor will deliver some Q. So if we don't have the capacitor, the amount of Q that taken by the load is the same as the amount of Q taken from the supply. So we are going to say this is Q old. Old means before of adding the capacitor or before of improvement or for power factor improvement. So let's refer to that by old. And if you have a capacitor added to your circuit right now, so let's say the amount of reactive power that the capacitor will provide is called Q added. So in this case, the total amount of Q would be Q new. And from here, guys, we can say Q new equals Q old minus Q add. So this is just if you apply the Kirchhoff current law here. So it could be like current because the direction is typically like current. So just apply the Kirchhoff current law to the reactive power as well. This is fine. So we can say Q new plus Q add equals Q old. Okay, or Q new equals Q old minus Q add. If you would like to calculate the amount of power before adding the capacitor, so let's say S, or the apparent power seen from the source here, we can say S old, for sure, S equals P plus or minus JQ. So if you would like to get the absolute value, so we can say S old equals square root P square, which is the active power absorbed by the load, plus Q old square. And here in this power triangle, this part refers to the Q old, and here on the horizontal axis we have the P, the active power, and this is the old apparent power S. Now if you added the capacitor here, we will have some added Q. And for sure, guys, the added Q of the capacitor is in the opposite direction of the Q inductive. So in this case, the total Q would be this term, because Q added here is in the opposite direction. So this is the Q added of the capacitor. So this part is the Q added by capacitor. So this is due to capacitor. This is due to inductor. And the net Q will be this part from here to here, which is nothing but Q old minus Q add. Okay. So in this case, guys, our new apparent power S new would be square root P square plus Q new square. So if you would like to know the new power factor, you can get it from the new triangle. So this is the new triangle of power. So the new power factor is nothing but cosine this angle. So this is the angle of the power factor. How can we get it? Easily you can get it by means of cosine inverse P divide S nu, or it could be sine inverse of Q nu divide S nu. So you can use whatever function you need. It's nothing but a triangle. So we can say the power factor nu equals P divide S nu. And S nu equals square root P square plus Q nu square. So by the end, power factor nu equals cosine the angle, which is tan inverse of Q nu divide P. So we can say if this is angle phi, so we can say tan phi equals Q nu divide P. So tan inverse Q divide P equals phi. So this is the power factor, guys. The power factor nu equals cosine tan inverse Q nu divide P. Okay. So this is how to calculate the new power factor after correction. My question, if you provide amount of Q added here equals to the old amount of Q, so this means your Q new would be 0. And this case means you don't have any Q absorbed from the power supply. And in this case, you would have S equals P. And this means the angle phi equals 0 and the power factor cosine inverse 0 equals 1. So this is called unity power factor. So this is the maximum power factor that we can have, correct? You cannot have power factor more than unity, because by the end, power factor is nothing but active power in per unit, or cosine and angle. So there is no cosine more than unity in our life, correct? So this is, guys, how can we make a power factor correction? This is just what I already discussed with you. If you have the added amount of Q equals the Q old, so this means the amount of Q new absorbed from the grid equals 0, and in this case, this would be the S new, which means Q new equals 0 and power factor is unity. Let's solve this example together, guys, and after solving the example, we would make some comments to understand the benefits of power factor correction. So in this example here, guys, we have a single phase motor connected to 400 volt, 50 hertz supply. So 50 hertz. So this example, guys, from a book in Europe. So the supply frequency in Europe is 50 hertz. Okay, from Europe or Middle East. So this is the frequency in the Middle East or in Europe. It's 50 hertz. Okay, you know that the supply we have here is 60 hertz. So whatever the frequency, so this load is connected to that supply and takes 31.7 ampere. So the motor takes 31.7 ampere at a power factor of 0.7 lagging. 0.7 lagging means the power factor is lagging, means the load is inductive. And for sure, since this is a motor, it should be inductive. Only we have a different concept for synchronous motor. The power factor of a synchronous motor can be controlled, and we will discuss that in the topics of the synchronous motors. However, in general, guys, if you have any problem, any kind of any undefined motor type, so we can consider this AC motor as induction motor, and we can consider this as power factor or lagging power factor or absorbing reactive power. Okay. The only exception is for a synchronous motor, it could have controlled power factor, but this is not in our topics today. So the power factor is 0.7 lagging, current is given, volt is given, frequency is given, so we have everything about this load. What is needed here? Calculate the capacitance required in parallel with the motor to raise the power factor to 0.9 lagging. So now, guys, we have a supply, we have a motor with 0.7 lagging power factor, and we would add a capacitor to make this power factor equals 0.9 to improve this power factor from 0.7 to 0.9. Okay. So simply we can follow the relations we just described in the previous two slides. So firstly, let's calculate our active power of our load, which is going to be constant. Whatever the power factor correction, the power has to be the same. So we can say this is single phase. So power equals V times I times power factor. So volt is 400. Current is 31.7. Power factor is 0.7. So this is the amount of active power needed from this load, for this load. What about the reactive power without capacitor? So we can calculate the reactive power by means of the power factor. So you know that reactive power equals VI sine phi. So VI sine, the angle phi can be calculated as cosine inverse power factor. So 400 times 31.7 ampere sine cosine inverse 0.7. So this would be the amount of reactive power taken from the supply. Now, we need to have a capacitor to make the new power factor equals 0.9. So this means, guys, let me draw the power triangle. So this is the first case, P, Q, and this is S. So we have Q now equals 9 kilovar. We have P equals 8.87 kilowatt, and S, we didn't calculate S, no problem for the time being. And this is, I'm gonna say this is phi 1, and cosine phi 1 equals 0.7. For the next case, guys, I'm expecting the angle to be smaller because the power factor has been corrected. So let me change the color here of my pen. So I'm gonna say this is our Q new, and this is gonna be the new amount of S, and this is here angle phi 2, and cosine phi 2 equals 0.9. Now I need to calculate the capacitor. In order to know the capacitor, guys, I need to know the amount of added Q. In order to know the amount of added Q, so I need to know what is the amount of Q of the 0.9. So we can firstly get the amount of Q for the 0.9. So you have now the power factor of the new case. So what is Q new? So we can get Q new from here, guys. So Q new equals P tan angle. P is the same. Tan this new angle equals Q. Q new. So this is here Q new. So here, guys, it's P, the same amount of power, tan, cosine inverse power factor new. So this would be now the new amount of reactive power. What is the difference? What is the added Q? The added Q would be the difference between the old and the new amount of reactive powers. So the added Q is Q old minus Q new, which is going to be 4756 VARs. So this is now the amount of reactive power added from the capacitor. How can we calculate the capacitor? Simply, guys, you know that Q equals V squared divide XC, and XC equals 1 divide omega C, and omega equals 2 pi times frequency. So we can get the capacitor from here. So if you get the relation, guys, you will find that C equals Q added divide V squared omega. So this is the amount of Q added, V squared, so 400 squared times 2 pi F, which is 50 hertz. So we have here a capacitance of 94.6 times 10 to power minus 6 farad. So we have 94.6 microfarad capacitor needed to provide this reactive power. Okay. So this is just a sizing problem, but we don't see here what is the benefit. Still, the benefit is not clear here, guys. Let me show you one thing. Here in this problem, we just calculate. I'd like to calculate S for this problem, guys. So I'm gonna use now my calculator with you, and we can see the capacitor. Sorry, we can see the amount of current needed for this new case. I'm going to create a new slide here with you. Just grabbing these numbers here. So this is just reference to us to okay. Now let's see, guys, what is the new current we have. So what I would like to calculate here, calculate I new. What is I new? The new amount of current. How can I get that? Simply, you know, guys, that S equals V times I conjugate. And if we just consider the absolute values, so S equals V times I, V absolute value times I absolute value. But I'm going to say S new and I new. For sure, the volt is going to be the same, guys. The volt, the grid volt is going to be the same, or we can assume that volt is the same. Okay. Okay. So it's like, yeah, let me say it's not for undergrad to say if the volt is going to be the same or not, because injecting or changing the reactive power would improve the volt, but this is for the isolated systems. But this is another topic. We may discuss that in the synchronous generator when we discuss the dynamics of the synchronous generator, we will discuss something related to that point. But for a load, for the grid connected load, we have a load. The power factor correction will not affect the supply volt, or we assume that the supply volt is constant all of the time. So we have the volt, guys, equals 400 volts. And we need to calculate I nu. So I need to get S nu. I can get S nu by means of S nu equals square root P square plus Q nu square. Is it correct? So we can say P equals, we calculated P here, it's 8876. So 8876 square plus Q nu is calculated here 4298. 4298.84 square. Let me calculate that using my calculator. So 8876 square plus 4298.84 square, all under square root. So the result is 9.862 kilovolt ampere. So this is the new S. I would like to calculate I now, so I can say I nu equals S nu divide V. So 9.862 times 10 to power 3, because it is in kilo, divide 400. So the answer is 24.65 ampere. The question, what was the first current? As you can see here, guys, the current was given, sorry. So the current was given 31.7. So this means I nu is less than I old. So this means the amount of current absorbed from the supply has been decreased when we improve the power factor. So who got the benefits now? Who got the benefit? The customer or the distributor? The company that distributes the power. Because you as a customer will pay the same amount of money, which is depending on your active power absorption. The active power absorption is the same. So you absorbed already 8876 watts. So you will pay for this amount. So adding capacitor will not help you to reduce your power bills. You will pay the same amount. But the distributor will supply you with less current, which means by the end, the supply do not to have large conductors or cables to provide you with the amount of power you need. So this saves money for the distributor. This saves money for the grid distribution. Okay, guys. So this is the benefit of improving the power factor. So when you improve the power factor, the amount of current absorbed from the supply would reduce, and this would reduce the stress on the distribution network. Okay, so this is the main benefit of reducing the of improving the power factor for our low voltage networks. Okay. Another solved example here, guys. So here in this solved example, we have a solenoid coil with a resistance of 30 ohm and inductance of 200 millihenry. Is connected to 230 ampere, sorry, 230 volt AC, 50 hertz supply. So we have a solenoid. So a solenoid, guys, is nothing but electromechanical system. When you supply this solenoid, it will have a plunger inside. This plunger will move when you supply this coil. So what is needed here? We need to calculate the solenoid's impedance. So solenoid's impedance, you have resistance, you have inductance, frequency is given. So it's easy to say the impedance is Z equals R plus JXL, and XL equals omega times L, omega equals 2 pi F. So it's very easy to calculate that one. So this is the first thing. The second thing is the current drawn by the solenoid. So once you have the impedance, so you can say I equals V divided Z and get the amount of current. Then the phase angle between the current and applied volt. So you need to get the angle, and you can get the angle by means of the power factor or the angle from the impedance. You have XL and R, so you can get the angle. Then the power factor and it seems here this is a typo here, the average power consumed by the solenoid. Okay, so this is typo, guys. And the average power consumed by the solenoid. So it's required to calculate the power factor and power. So there is no power factor correction here in this example, but this is just a direct example how to calculate the power and power factor. So very simple example, guys. So firstly, start with the impedance. You know that XL equals 2 pi FL. So 2 pi times 50 times inductance. So this is the XL. Then the impedance Z as absolute value equals square root R square plus XL square. So 30 square plus 62.8 square. So this is the amount of impedance we have here. So I current equals V divided Z. So 230 divided 69.6. So this is the current absorbed. The phase angle, you can get it actually from the XR ratio. So tan inverse X divided R. So the angle is 64.7, and the power factor would be cosine this angle. So the power factor is 0.431 lagging. I'm answering this very quick because this is very simple AC question you already learned in AC circuits. Another way to calculate the power factor, guys, is the absolute value, R divided the absolute value of Z. So 30 divided 69.6, so it will give you the same value. And it's lagging. Why it's lagging again? Because this is inductive load. By the way, guys, if you, for any problem, if we ask, find the power factor, you have to identify the type of the power factor. If you said only 0.431, so this is half of the answer. This is not full answer. Full answer is the power factor magnitude and type, except only if it is 1, because 1 is unity, okay? Or 0. Sorry, 0 even, 0 you have to mention lag or lead, okay? So the only exception is for unity power factor. Part E, okay, so this is not typo, this is part E, so it seems like it's like, yeah, when we make it, it's converted to this special character. So part E was the average power, so you know that power equals I squared times R. Take care, guys. All of the time, average power depends on the resistance. whatever reactance you have in your circuit, it's not affecting the active power. So the active power all of the time is going to be resistance dependent. So I square times R. For sure, I square times R in case of single phase. In case of three phase, it would be 3 times I square times R in case of symmetrical three phase loads. Okay. Now we almost covered the part of the power factor. Let's start discussion on the three phase systems. Firstly, guys, for three phase systems, you know that we have balanced and unbalanced. But in electrical machines, which will be described in our course, we all of the time consider that three phase are balanced. So for any three phase machine, we consider that the three phases of the machine are balanced. Balanced means the three phases have the same impedance and absorbs the same amount of current with a phase shift of 120 degrees. Okay, so this is the meaning of balanced three phase system. So for a balanced Y connection, so this is the first connection here, guys, we have, which is Y connection. So this is a Y connected synchronous generator, for instance. So what you can see here is three phase windings. Neutral point is not connected by a wire to anything else. But here in this diagram, neutral point is connected. So the exact translation is going to be like that. Okay, so this is four wire system. This is four wire system. So this synchronous generator, guys, the three phase windings are already wound inside the machine, and the output of the three phase windings, every phase will have two terminals, and these two terminals are connected outside like that. Three starting terminals A, B, and C, and three end terminals are connected to the point little n, and then connected to a fourth wire. So this is now the generator symbol. So we have three AC sources, A, B, C, and the neutral wire. The waveforms are nothing but three-phase voltage waveforms with a phase shift of 120 degrees. So this is 120 degree. This is here will be 240 degrees, and so on. So this is the three-phase system in case of Y connection. If you would like to draw the phasor diagram, and this is very important in our course, so we have to draw phasor diagram for most of our topics. So you have to understand the concept of drawing phasor diagram. So for the three-phase system, guys, we have, for instance, in the time domain forms, we have Vn equals V maximum sine omega t, V maximum sine omega t minus 2 pi over 3, which is 120 degrees. And then Vcn equals V maximum sine omega t minus 4 pi divided 3 or plus 2 pi divided 3. It's the same. So we can say the Vn equals V maximum divided root 2. So V maximum divided root 2 is the RMS value. And we describe the AC quantities all of the time by RMS. We do not describe the AC quantities by maximum values. So the 110 or 115 volt you have at the supply at home is RMS value. It's not peak value. Okay. So we have now RMS value VA at angle 0 and minus 20 and plus 120 or minus 240. Okay. So the three voltages VAN, VBN, and VCN are, as you can see. What are the line voltages? If you would like to get line volt from phase volt in Y connection, simply if we go back to the circuit here, I have here VAN, so this is here VAN, this is here VBN. If you would like to get VAB, so it's gonna be this loop. So this means VAN minus VBN. Let's go to the phasor diagram and do this operation. So this is VAN, this is VBN, so minus VBN is gonna be in this direction. So this is minus VBN. Adding these two vectors together will provide you with the resultant vector here. So this is VAB. Okay, so VAB now is shifted 30 degrees from VAN and with a magnitude equals √3 times the phase. For that, you will find when you convert from phase to line in Y connection, multiply the phase value times √3 and add 30 degrees to the phase angle. So this is the rules for ABC sequence in Y connection. What about sequence, guys? We didn't discuss sequence. So sequence means if you stand right here and observing the system, and the system is rotating. Rotating how? Rotating in this direction, counterclockwise. So you will see VA, then VB, then VC. Okay, so this is called ABC sequence. So the guy stand up here and observing the rotation of the vectors, he would see VA, then VB, then VC. Okay, so this is called now the ABC sequence. If the guy figure out A, then C instead of B, so this is called called ACB sequence. So this is called the sequence. How the sequence is changing, guys, we will learn that when we discuss the synchronous generator topics. So the sequence can be changed from the supply or generator by reversing the motion of the shaft of the generator. So it would provide negative sequence. So this is called positive sequence. So positive sequence is ABC. Negative sequence is ACB. Okay. Here we have the ACB. So as we just discussed in the previous slide, so this is A, this is C, this is B. So the difference is instead of having VC at angle plus 120, it's at angle minus 120. So these are the differences between ABC and ACB. What about the delta connection? Inside the generator, we can connect the machine as delta connection. So in this case, how can we make the delta connection? And we will end up with this slide here, this session. So if we have three-phase windings like that, this is start, and these are the ends. I'm gonna connect in different color to make it visible to you. So for delta connection, connect the end of the winding to the start of the next winding. So this is the end of the winding, connect this to the start of this winding. The same here, this is the end, connect that to the start of that winding. The same here, this is the end, connect this to the start of the first winding. So this is called the delta connection. But for the Y connection, if we go back to the Y, right here, I'm gonna draw the same for you. If we have the three windings here, so connecting Y connection means either start or ends. Make short between starts or ends. So I'm gonna make short between the ends and supply or connect starts to the supply. So this is called Y connection. And here in our case, we have also extra neutral wire because we have 4-wire system. So this is the 4-wire four-wire Y connection. We don't have 4-wire connection in delta connection. Delta connection all of the time is 3-wire connection. Okay, so this is the delta connection. I don't like to make the class more longer than that. We will continue discussing the delta connection in the next session, guys, and we will discuss more about the power calculations in 3-phase systems. Thank you so much, and have a nice time.